from the last lecture. We have already completed our electrostate. Uh, I am unable to cover all the topics as I told you guys earlier, but we are doing the most important topic on the overview of our exams. As you know that the dates have been already declared, so we have not much time, and that is why we are just doing some most important topics. And I'm sure if you guys will practice these topics properly, you can get the title. You just need to do some hard work. Yeah. So starting with these words, and this is my lecture number 7. In the last lecture we have discussed about some introduction of magnetostate. Now we'll move ahead, and the table of content for today's lecture is we'll review magnetic field, like just a brief study about magnets and their properties. Then in the last class I've told you that we'll do applications of Biot-Savart's law in our next lecture. So yes, we'll do the most important applications and their questions too, because this topic is quite important. Mostly one question in each paper is coming from Biot-Savart law and applications of Biot-Savart law or Ampere's law, or by combining both. So what type of questions are coming and how to solve them, we'll also discuss in this lecture. Then we'll study about solenoids, toroids, and magnetic materials, and the boundary conditions in magnetic materials only. We have studied many types of boundaries yet, like we have studied boundary conditions in electrostate, we have studied the boundary conditions for polarization, we have studied the boundary condition for method of images. Now we will be study the boundary condition for magnetic materials, and one more time we will study some boundary conditions when we will be discussing on uh, electromagnetic theory, like in Maxwell equations. So yes, at last we'll do some questions. So yes guys, this lecture is quite important, and I'm starting now. So just reviewing the magnetic field. So you guys know that magnets have always dipoles, no monopoles. We have discussed this thing in our last lecture too. And magnetic field exerts a force on moving charges, like on currents. Magnetic field is exerting forces, not forces are generating magnetic field. Okay. So magnetic field exerts a force on moving charges, and that force which magnetic field will exert is perpendicular to both magnetic direction, the magnetic field direction, and the velocity, the direction of motion, velocity v. Okay, if the charge is moving in the x direction and you are applying magnetic field in the y direction, then the force will always be in the z direction, perpendicular to both of them. Yeah, because of this perpendicular direction of force, a moving charge particle in a uniform magnetic field moves in a circle or spiral. So we now know that the direction of force is perpendicular. So because of that perpendicular force, the charge particle starts moving in a circle. Now it will not move in a straight line path. It will form a circle or a spiral type of shape. Okay, so the charge is moving, and that is why it is generating a current. So we can write the force in terms of current, but since current is not a vector, it leads to a kind of massive way of writing the equation. We can understand it by these diagrams. So this is a magnet in a big form. If we are cutting this magnet into pieces, and we have done the smallest one, we have made the smallest pieces, then also there will be two poles, the north one and the south pole, north one and the south one, because no monopoles exist in magnetic field. The second one was the force is perpendicular to the V and B, so we can write it as FB equals to Q V cross B. This Q is the magnitude of charge, V is the velocity of charge, B is the magnetic field applied on the charge, and FB is the magnetic force. So yeah, how it is moving in a spiral path. So you can see in this diagram. Uh, let's select a pointer. Yeah, so look at this diagram. So if you have applied the magnetic field, the direction of magnetic field is this cross means. I have told you what does it means by cross and what does it means by dot. A dot means inside to the page, a cross means outside to the page. So the direction of magnetic field is outside to the page, or outside to the plane, and this one is your charge, this one is your charge, this one is your charge. And the charge is moving in this direction. This is the direction of velocity. It initially it was moving in this direction, and we have applied a perpendicular magnetic field, so one force will generate inside this circle. So at every position, at every point, when charge is here and when charge is here, at every point the force will be towards the center, and that is why a center is generated already and the charge starts moving in a circular path. So these are some basics from magnetic field. This one is spiral path, you can see in this diagram. If a proper circle is not making, the charge may move in the spiral also. Yeah. So what is the magnetic field that is caused by current? If we are applying current to any wire, then the wire may generate the magnetic field. So how we can calculate and what will be that magnetic field? So it's possible to make a magnet by winding wires in a coil and running a current through the wire. How? So this is a coil wire which we have wounded with a small this we can say screw or like that. So we have wounded a wire around it. Okay, so this wire is when we are applying some current, like we have added some battery here and the current is moving. So in the wire, in nearby this wire, a conventional magnetic field will be induced. Okay, so by the current, the magnetic field is caused, and yeah, we can say with this also, this is your electric weighing. Uh, we can weigh 100 of tons and even more by using this method. Okay, so yeah, what we are understanding with this diagram is, look at this one. This is your magnet, a permanent magnet, and it has tremendous number of atoms. Like I am saying, it has n number of atoms. Okay, and those atoms have some small dipoles, because in a magnet every piece is a dipole, not a monopole. So there are small amount of dipoles, but we are unable to see them. Okay, we are unable to see them. So what we'll do, if we are applying some current, like we have generated some field around this magnet, and then the dipoles starts aligning in the same direction. The dipoles in the magnet start aligning in the same direction. You can see all the directions are in this one, like we can say negative x-axis. So this, in this way, the strength of magnetic field created by current depends on the current as falls off as 1 over r square. Once a small question was asked in your GATE exam, so the answer was 1 over r square. So this is the basic concept how magnetic field is caused by current and where we can use. This is an electromagnetic crane, and electromagnetic weight is it also looks like the same, so it is an electromagnetic crane. Yeah, so this is 1 over r square, you have to remember. Next I am moving to the Biot-Savart law, and with using this Biot-Savart law we will do some applications. So yes, what is Biot-Savart's law? We have studied the Biot-Savart law in our last lecture too. So basically, the Biot-Savart law is applied on some magnetic, having some magnetic material of elements, and uh, we calculate with this law the magnetic field, the value of the magnetic field at any point for that current conducting element, current carrying element. Yeah. So in this diagram, you can see there is a wire, and we are taking some surface element ds of this wire, and we have to calculate through this wire the magnetic field on this point B. Okay, so this is the formula of our Biot-Savart law. This dB is equal to mu naught over 4 pi. Mu naught over 4 pi is a constant. Mu naught is the permeability of vacuum. 4 is a constant and pi, you know. And I ds cross R vector over R square. I is the current and ds is the surface area element. Always remember that the area element is always perpendicular to that surface. Okay, if you have to draw some area element now, then just draw tangential to that surface. Okay, so that with the less error you can find out the answer. Yes, so this is the Biot-Savart law. And yeah, I've told you it is a permeability constant 4 pi into 10 to the power minus 7 Tesla meter per ampere. It has the units, and c is your speed of light, can be written as 1 over under root epsilon naught mu naught. So yes, here is a point. You can see the point, orange one. This was a point into the page. I am considering this point out of the page, above the page. Okay, so dot. So what we'll do, we have to do just calculate the magnetic field on these both now. So yeah, so the distance we'll consider the same. If it is r, it is also r. Okay, and here dB will be obviously out of the page. So how can we find out, looking at this wire, that the magnetic field will be into the page or out of the page? So there is a rule called right hand rule. You can see two diagrams, A and B. Just first look at this diagram B. You have a wire. Just put a pen in your hand and thumb like this. Hold that pen like this, and if your thumb is in upper direction, then the curve of fingers will show the direction of magnetic field. The curve of fingers will show the direction of magnetic field. Now if your point is on this side, left of this page, then the finger will cover that point. So the direction of magnetic field will be out of the page. If your point is in this side, right of the page, then the fingers are able to combine that point in the hand. So this will be into the page. Again, look at this diagram A. Now hold the pen vertically in opposite direction. Now the finger is in this direction, downward, and curl your fingers. The curve of your finger is telling the direction of conventional magnetic field. Okay, so in this case, if you have some point this side, left of your hand, left of your pen, left of your wire, then finger will cover this one and the magnetic field will be into the page. And if the point is right to this, then it will be out to the page. So this is your right hand rule. I hope you guys are able to understand. If you have any query regarding to any topic, you can stop me anytime. I'll be happy if you ask me any question. Okay, yeah. So otherwise, if you will not ask, I will ask. Hmm? So this is your right hand rule. So yes, here is a question. You guys will told the direction of magnetic field. So the question is, which drawing below shows the correct direction of magnetic field B at the point P? And there are five conventional situations and four options you have. So just tell me within 10 seconds. Look at this image. You now know the right hand rule. Just apply the rule. Imagine your hand on these lines and just tell me the answer.
Ma'am, third one.
Who is saying that? Hasmukh. Okay. और कोई? Yes, third one is the right answer. Good job, Hasmukh. So, guys, if I ask you questions now, then please try to reply. I am not taking any type of test. I am not judging your ability. Just I am happy if you answer in the class. If you can share your views in my class, I'll be happy. So please interact with your teacher so that you can learn more and more. Okay. So please do
Hello, ma'am.
reply.
Am I audible, ma'am?
Yes, you are audible.
Okay, ma'am. I am trying to ask question, answer, but I don't know what happened.
Okay, no problem. Yeah. So moving ahead. So yes, the answer of this question is three. Okay, see, three. Due to a long straight wire, we have to calculate magnetic field now. So the condition is that we have a straight wire. You can see in this diagram. This is our straight wire, and we have to calculate the magnetic field due to this straight wire at any point. The point may be anywhere near to the wire. So we are considering a point P here. Okay. So just apply your right hand rule. Just hold this wire. Just imagine the wire in your hand, the thumb in the upper direction where this blue one arrow is. Okay, just hold your thumb here and curl your fingers. You will see that your fingers are coming like this way. They are coming like this way. Yeah, this way. So if the point is this side, then it will be out of the page, and if the point is this side, then it will be into the page. So our point is this side. That is why they are putting a cross. Yes, cross means into the page. So the direction of magnetic field now you know. So for this type of problem, we use Biot-Savart law. So this is an application of Biot-Savart law. So what we have to do, we know the mathematical formula of Biot-Savart law, that is dB equals to mu naught over 4 pi IDS cross R over R cube. Yeah. So what we will do, just add up all of the contributions ds to the current, keeping track of distance r. I hope you can understand the line. What we are doing, we have just divided this whole wire into small pieces of area element ds. Okay, some small pieces. Okay, and uh, we are considering that one piece as our current element. For that one piece of area ds, we will first calculate the value of b, then we will just add all the contributions of all the ds. Yes, so we have to do this. So while we are adding those all, I have told you that summation means adding. Okay, so we'll do summation obviously. So if I am doing summation to this side, then this summation or integration of d will cancel out each other. So I am getting b. Okay, b equals to, now we have not told here that the length of the wire is like this. So I am considering minus infinite to infinite. Okay, so by putting 2 outside, I can write it as 0 to infinite. Okay, this is the mathematical formula. I hope you know that. We can convert it in this way too. So just put the value of dB. dB, you know, this one is your dB. And mu naught I over 2 pi 0 to infinite. Now, what is this? R sine theta ds. What is this? R sin theta ds over r cube, so you know that is in the formula. You have just written down the formula here, and I is here. So what is this r sin theta ds? Okay, so we have to solve this one. This is our ds cross r. ds cross r means vector multiplication of the area, direction of area element, and the direction of your area element to the point, that is r. So this is your ds and this is your r. So the angle between these two is theta. You can see in this diagram. Yeah, and it is a cross product. So you can write sine theta. So that is r sine theta ds. I hope you are able to understand. Now, using the Pythagoras theorem on this triangle, we can calculate the value of r. So the r will be under root r square plus s square. Okay. So again, using the Pythagoras terms, I am getting r sine theta equals to capital R. So just I will put all these values into the equation above, and by integrating, I am getting this value, this big one. B equals to mu naught I upon 2 pi r s over under root r square plus s square. The limit is from 0 to infinite. When you guys will apply the limit, you will get the answer B equals to mu naught I over 2 pi r. This is your answer. This is your magnetic field due to current in a long straight wire. Okay, so this one is important page. Just always keep this formula, means this result, and this diagram in your mind while you are solving the question. I hope you are making some short notes of each subject. So when you will make short notes of your magnetostate now, so the method you will use is just make the diagram and put the formula besides it. That is enough. Okay, so that you can remember all the things together. Next one is magnetic field at the center of a circular arc of wire. In the last class, Hasmukh have asked one question, that if the wire is circular, then how we can calculate the magnetic field? You have asked, na Hasmukh? So this is
Yes,
your
ma'am.
answer. Yeah, this is your answer. This is the application of Biot-Savart law, another application. And in this application, we have turned the wire into a circle. Okay, the circle may be a semicircle. The circle may be a part of that wire, a small part of that wire, may be having some curve. Okay, so for any circular wire, we will calculate the magnetic field. So this is the recipe you can watch. So this is the formula of your Biot-Savart law, that is dB equals to mu naught I, mu naught over 4 pi IDS plus R over R cube. So suppose whole circle was there, a whole circle was there, and the C is the center of that circle, R is the radius of that circle, and we are taking some element of the circumference of that circle, just some element. I have cut it down. Okay, and the angle for two far ends is phi. The current for this area element is I. So it is the same situation we have to follow in our Biot-Savart law, because the Biot-Savart law says for a current carrying conductor, we can calculate the magnetic field at every point. whether it is on center, whether it is on surface, whether it is on outside to the circle, whether it is on inside to the circle. Yeah. So the same we will do. D equals to integral 0 to 5 dB. Just put the value of dB, and we are using the circular arc. So we'll use cylindrical coordinates. For circle, we will use cylindrical coordinates or circular coordinates. ds equals to rd5 will be, and you can just solve it. So the final answer you will get is b equals to mu naught I over 2r. This is the magnetic field at the center of a circle. The circle must have some current carrying element. Otherwise, the formula will not exist. Okay, so two formulas you have learned. The first one is magnetic field due to a long straight wire, mu naught I over 2 pi r. Magnetic field at the center of circle, mu naught I over 2r. Just a minor difference. The pi was there and here is not any pi. Okay, so don't be confused. Just make some short notes and put all these things on the same place. Okay, moving ahead, the next application we'll study in Biot-Savart law is magnetic field for lines and arcs. So how would you determine B in the center of this loop of wire? You can see this loop. It has not a specific symmetry. It has some circle type of symmetry, then a straight line, then a circle, then a straight line, then a piece of circle, then a straight line, and then a piece of circle. Yeah. So these types of arcs and shapes, for these types of arcs and shapes, we can also calculate the magnetic field. How we will calculate? Let's see. So just divide them area wise, just cover them area wise, and just calculate some angles. This is like some difficult method. I'll tell you one easy method too. So yeah, if you are considering some center mid between, like I am considering a center here. So the by just observing, this is your r, this will be your 2r, and this is even far, so it will be a 3r. Okay, so so yeah, the perpendicular one, this point and this element is the perpendicular. So for the perpendicular one, the magnetic field will be 0. Always remember this line. Just note down somewhere or keep in your mind that for the given point, the perpendicular line carry the magnetic field 0. The perpendicular line carry the magnetic field 0. So here magnetic field is 0. Here magnetic field is 0. Here again magnetic field is 0, and here the magnetic field is 0. So yes, for the rest we'll use Biot-Savart law. For circular arc, mu naught I 5 over 4 pi r we will use. Yeah. So let's change it into a numeric problem. Say r equals to 10, I equals to 2.43 ampere, 95 degree means this much radian, 90 degree means this one radian, 70 degree means and. So we have B equals to, this is your value of mu naught. Okay, this is the value given, current I 2.43 angstrom. This is here I 2.43 angstrom, and this is your value of phi over the distance, phi over the distance, phi over the distance, phi over the distance. So for this area, angle is 90 degree. So the value of phi will be 1.571 radian, and the distance is 3r. Distance is 3r. And in the same manner, you can calculate. So at last, you will get 7.812 microtesla, the answer of your magnetic field. Out of the page, this one, and obviously into the page, it will be minus. So minus 7.458 mu t into the page. Yeah, what is the difference between these two? How we are getting the different values? So look at this first one. We have four areas, and to calculating out of the page, like we have not given any conventional direction of our magnetic field now, so we will do for both the directions, out of page and into the page. So for out of the page, we will just add them all. We will just add them all. But for into the page, the first three will be same. The first three will be same. Like if I am starting from this one, from this point, from this arc. So I have calculated this one. This is 0. This one. This is 0. This one. This is 0. Okay. We are moving from this side. And when the last curve is coming, this curve, then it have the conventional direction in negative side. Like it will move in this side. From this point, the direction will be to this side and this side too. So for any one curve, the direction will be changed. That is why a minus is coming. You will got to know about this when we will do some questions, more questions. Okay, don't worry. Yeah. So look at these three diagrams. You have to calculate magnetic fields from the loops. The three loops below have the same current. Rank them in terms of magnitude of magnetic field at the point shown. You have to put greatest at first place, then the less one, and at last the least one. Yeah. So just tell me the answer. You have 10 seconds. Just try to find out. Yeah, Shravya. How you guys are saying that the answer is C. Hasmukh and Shravya both can answer.
Ma'am. Okay, ma'am.
Uh,
It depends on phi and r, value of phi and r.
Yes.
So if phi is more, then
Yes.
B is more, and r is more, then B is less.
Less. Good. And Shravya, what will you say?
yes, ma'am. Hello.
Yes, I can hear you. Hello. Hello. Is someone there?
Yes, ma'am.
Okay. I think Shravya has got some problem, na? She's been locked out. Yeah, don't worry. So the C will be the answer, and you are right. The more the phi, the more the magnetic field, the less the R, the more the magnetic field. But the more the value of R, the distance, the less the magnetic field we can get. So for the question number 2, you will get the third one have the highest, greatest magnetic field, then the first one, and at last the second one. Okay, so let's move ahead. Now we will try to calculate force between two parallel currents. Look at this diagram. There are two wires. They are parallel, and we want to calculate the force between these two parallel wires. So a wire carrying a current in a magnetic field feels a force. You know that thing. Yeah. And when there are two parallel wires carrying current, the magnetic field from one causes a force on another. Yeah. So when the currents are parallel, the two wires are pulled together. And when the currents are anti-parallel, the two wires are forced apart. What does it mean? Let me tell you. I am saying that when the currents are parallel, the two wires are pulled together. That means if the currents have the same direction, the wire, this wire having the direction in this direction, current in this direction, this wire also having the current in this direction, then some attractive force will be generated between them, like this. You can see this arrow now, this white arrow, it is quite small. So the force between them in mathematically will be Fb equals to I L cross B. What is this L? We will learn it later on, and the force will be this type. Same for both of them. Now, if the currents are anti-parallel, just remove this force. Anti-parallel means the first one have the current in this direction and the second one having the current in this direction. You can see the arrow. Now, what will happen? The forces will oppose each other. It the first one is pulled left side and the second one is pulled right side. So they those are feeling opposite direction forces. So this is the type of force between two parallel conducting wires. You can see in this diagram too. It is quite easy to understand. So if I am taking two infinite wires, so we will cut some length of that wire for ease of doing or solving the question. So the conventional length will be L now. Okay, L. This is your wire A, this is your wire B. The distance between those two wires is D. Now, if we are applying the current in this wire like this one, IA, this one, IB, this one, then here will be a magnetic field BA and the force will be applied in this direction FBA. This is all will be due to the current IA. So when one wire having the current IA, the force will be generated on another wire. Okay, so the force FBA will be equal to IL cross BA. Now L is the length. Okay, so now you got to know the formula. This is your magnetic field for straight conducting wire. So now we can turn it into mu naught IA. We know now that the current is for A. So mu naught IA and 2 pi. R was the distance. So here D is the distance. Or I can write the force as mu naught IA IB L upon 2 pi D. These are some important formula. Okay, now next question. Which of the
Ma'am,
yes,
ma'am, previously we studied for magnetic field of straight line also mu naught I by 2 pi a, no ma'am. Previous one,
yes,
2
yes,
pi r. For
yes,
both parallel current lines also
yes,
same formula, ma'am.
yes, yes, yes.
I mean,
The they
any
have
like
made
not
of
only
same material. Yeah, what are you asking?
it can be like here two parallel currents there we are studying now. It is that formula is applicable for both. I'm asking, ma'am.
Yes, it is
Straight line.
applicable for both. Yes, if we'll talk about this IB, na, the current on this wire B. So
Okay.
I will put it here IB only.
Okay.
Will not
Okay.
change the specific formula. The formula will be changed. I'm just taking an example.
Okay.
Okay.
Okay, ma'am.
So yeah, just solve this question and tell me the answer. Which of the four situations below has the greatest force to the right on the central conductor? Just tell me what will be the answer. It is quite easy. Just look the direction. Dot means outside the page. Cross means into the page.
Ma'am, A, first one.
Anyone else? The answer will be fourth, not A. D. 4 will be the answer. Just look at these four diagrams. Just observe these that this inward and outward will cancel out each other. Again, this inward and outward. Now, we are getting only one element of magnetic field. Just like that, here we are getting only one element. Here also we are getting only one element. But here, one and one will be cancelled out, and we are getting three terms of magnetic field we will get now. So the greatest force will be in this fourth configuration. Yes. So okay, just clearing the concepts. uh, I'm bringing these questions next. Ampere's law. We have studied briefly about Ampere's law in our last class. Now, I will be discussing the Ampere's law here because we have to study solenoid and toroid. So the solenoid and toroid are the applications of Ampere's law. That is why we are studying it again. So you know what is the Ampere's law, you know what is the Amperian loop. Okay, anyone can tell me what is the Amperian loop? This one, Amperian loop. What is the Amperian loop? Come on guys, you know the answer. Just reply. Okay.
Any closed loops, ma'am?
Yes, any closed loop, but what type of loop? Conventional loop we will make around any current conducting element, current carrying element to apply our Ampere's law. Like Gauss law, we use some symmetry now, and as like that, to using Ampere's law, we make a symmetry, and that symmetry, that loop, that cover, that imaginary symmetry is our Amperian loop. Okay, so the rest thing you know. And that is why I am moving ahead. Just this is your Ampere's law, you know that this is your Amperian loop, the direction of integration, the direction of magnetic field, area, element, current, you know all these things. Okay, so the magnetic field outside a long straight wire with current. So we have already used the Biot-Savart law to show that we know that B equals to mu naught I or 2 pi r. Now, can we use Ampere's law to solve this type of question? Yes, we can use. We'll make an Amperian loop. To use Ampere's law, I've told you that we will make a symmetry called Amperian loop. So for a wire surface, we'll make an Amperian loop. All the conventional parameters we will use. We will apply Ampere's circuital law, and we can also find out the answer. So the answer will be like that, and this will give the same expression. B equals to mu naught I over 2 pi r. These two are same. This is what we were getting from Biot-Savart's law. This is what we are getting from Ampere's law. So only one formula you guys have to remember. Either you are calculating it by Biot-Savart's law or you are calculating it by Ampere's law. You will get the same answer. Now, magnetic field inside a long straight wire with current. Now we are moving ahead towards the concept of solenoid and toroid. So if we want to calculate magnetic field inside the wire, inside the surface, inside the current carrying conductor. So we know that the current is evenly distributed over the cross-sectional area of wire. So if we have some wire, so we will use cylindrically symmetric. We will use the symmetry of cylinder. Okay, we will draw an Amperian loop for greater than this radius r. So this outer one is our Amperian loop, and using this Amperian loop, we have to calculate some first of all the enclosed current in this loop. So the enclosed current I enclosed will be equal to I, the area of the wire upon the area of the Amperian loop. Using this formula, you can get your I enclosed. Just you have to put the value of I enclosed now in this Ampere circuital law formula, and you can get the result. This will be your magnetic field inside a straight wire. You can calculate the same result by using Biot-Savart law too. Okay. So yeah, when we'll discuss on this graph, once a question have been asked in your net exam from this graph, there were four options, and the question was same: how does the magnetic field varies inside or outside a long straight current conducting wire? So there were four options of graphs, and this one was the right one. Okay, so for inside it will be proportional to r, so a straight line. For outside, it will be proportional to 1 upon r. From the formula also, we can get the same results. Moving ahead towards the solenoids. What are the solenoid? First of all, the question arises, what is this solenoid? So you can see a diagram. This is something spiral type of shape. Many of these spirals combining together and making some spring type of geometry. You must have seen any spring. Okay, so this is a spring type of geometry. If at each helix of this wire there is some current I. I am applying some current on this side and this side, either this side. So it is carrying some current I. So due to the current, we know that if any magnetic material is carrying the current, it will generate the magnetic field. Okay, so some magnetic field will be generated inside this solenoid. Some magnetic field will also be generated outside to the solenoid. Okay, so we want to just calculate the magnetic field inside and outside the solenoid. So we saw earlier that a complete loop of wire has a magnetic field at its center, and that is P equals to mu naught I over 2 pi. We can make the field stronger by simply adding more loops. We have added like n loops. I can say n loops are there. A many turn coil of wire wheel current is called a solenoid. You know that we can use Ampere's law to calculate magnetic field inside a solenoid. The cross section view of solenoid is looking like that. You can see this. This is your loop. This is another loop. There will be another loop. There will be another loop. There will be another loop, and so on. And the magnetic field lines will be generated inside. Like, let me draw some lines. If yeah, so this type of magnetic field, one line, then another line, inside it is going, है ना? Inside. I can't make it inside, है ना? So you have to imagine those are going through inside of this solenoid. Okay. So what is happening when we are watching the cross-sectional view of this diagram? Then it is looking like this one. Okay. So the field near the wire is circular, but farther away the fields blend into a nearly constant field on the axis. You can see this one. Near some points it is circular, it is circular, it is circular, it is circular. When we are getting further and further, they are bending, and at last they have been straightened out. They are now straight lines. Okay, so actual field looks like this one, this picture. This is your actual field. Now suppose some point is here, the point is P1, and you wish to calculate magnetic field on this point. So what will you do? You will use this type of symmetry, just two walls of your solenoid, those straight lines of your magnetic field. We will imagine some rectangular frame, half of the above the surface and half frame we have dipped into this solenoid in the surface. So for outer points, like on this point, on this point, on this point, on this point. For outer point, the magnetic field will be always 0. You have to remember all these things. The magnetic field for outer points will be 0. Now the symmetry is quite easy to solve. We have to solve for only inside the loop. Okay, so yeah, so we can get it like close integral b dot ds. Ds is what? The length. The length is h. We are considering h now. Look at this diagram. This is your h. So bh equals to mu naught ic, and I means current. Current is I into nh. Okay, so what we are getting, mu equals to b equals to mu ni or mu I n. Okay, this is for ideal solenoid. This is for this type of solenoid. This is for this type of solenoid. Okay, and now toroid. What is your toroid? You have seen the solenoid now. If you imagine you have a spring and you want to roll that spring into a circle, then that spring will be in the shape of a toroid. So if we are combining two sides of a solenoid and joint them, so we are getting toroids. Okay, so the toroid have this type of symmetry. We can say some points having the magnetic field outward to the page, some points will be magnetic field inward to the page. So this will be the formula we can get for the toroid. Inside the toroid, B equals to mu naught I n over 2 pi r. There are many formulas. I am adding one formula again, one formula again, one formula. Just make some short notes so that you will be not confused. Okay. So this was all solenoid and toroid. Now we have some coils and we have applied some current. Then also they will generate magnetic field. Na? So for this type of symmetry, current conducting coils, can we get the value of magnetic field? Yes, we can get the value of magnetic field by introducing the dipole moment inside that magnet. We know that a magnet has always two dipoles. So if there are there is dipole, then there must be a dipole moment. So what will be the value of dipole moment? Mu equal to NIA. You have to use in your magnetostate mu equals to NIA. And the conventional direction of current and the conventional direction of magnetic field you can find out by your right hand rule. Okay, all the things are just same. So yes, we have taken some part of your current carrying coil as a straight line. Some point we have assumed at this distance, straight distance at z, one end distance r. This distance will also be r. Na? Yeah. So for this conventional triangle, this one, I can get the values small r, capital R and Z, and by using the Biot-Savart law, I can calculate B on the axis of current carrying coil. Now, when we wish to calculate the magnetic field on the axis of current carrying coil, we will just we will just turn apart this dB into two parts. dB perpendicular means perpendicular component of magnetic field, and dB parallel component of magnetic field, and a conventional angle alpha. So the parallel angle of magnetic field and perpendicular angle of magnetic field will combine. When we'll combine them both, we can get the magnetic field dB. So not much questions are coming from this type of symmetry. So just I'm doing directly. dB perpendicular will be like this, and you can calculate all these things. So B will be integral of dB perpendiculars. At last you will get this formula. this one. Bz equals to mu naught I r square 2 over 2 r square plus z square is to the power 3 by 2. And if the distance is 0, means on the surface, like the point is here only on the surface, then what will be? Mu naught I over 2 pi. This is the same case of magnetic field of straight current conducting wire. There is the question, you have to calculate the magnetic field outside a toroid. So the magnetic field inside a toroid is using an ampere loop. You can calculate what is the expression for magnetic field outside the toroid. Anyone can tell me what will be magnetic field outside of this toroid? Like I am saying, I am putting a point P here. Can you calculate the magnetic field for this point? This is our P point. Just take 10 seconds and answer. Yes, so what is the answer? Okay, the answer is 0. No magnetic field outside the toroid. Just keep remember these things in your mind. Yeah. So this is the summary what we have studied till now. Magnetic field for a current carrying wire, dB equals to mu naught over 4 pi IDS cross R over R cube. Permeability constant, magnetic field due to a long straight wire, circular arc, and all and all and all. Yeah. So yes, I wish to continue, but wanted to know, you want to continue the class or I should stop here? Yes, Hasmukh, Sravya.
Yes, ma'am. Continue. No problem.
Continue, ma'am.
Okay. I'm continuing the class. So next, we'll study about magnetic materials and boundary conditions. Some few slides are left, so we'll just wind up it as soon as possible. So, what are magnetic materials? Magnetic materials means some materials having some magnetic properties. So, there are some materials you can see in this table, some diamagnets, some paramagnets, and some ferromagnets, and having different values of this mu r. Okay. So, if I don't know if you guys know or not, we can enhance the magnetic field by wrapping any type of wire around an iron core. Okay, and by that method also we can make a magnet. Okay, so the degree to which a material can influence the magnetic field is given by this relative permeability, that is mu r. This is called relative permeability. Okay. And for a free space, for a vacuum, the value of this mu r equals to 1, and hence it will not be affected on the, not put any effect on the magnetic field. Next, some important formulas will come. Magnetic flux density. What is magnetic flux density? In the presence of an external magnetic field, a magnetic material gets magnetized. Okay, so this property is referred to as magnetization, and the formula for your magnetization is M equals to chi mh. This chi is material's magnetic susceptibility. Okay, and this H is your magnetization, magnetic, yeah, you can write it as B also. This is B. And the total magnetic flux density inside the magnetic material in the presence of external magnetic field is this one, another formula. So if we are substituting the value of this N here, so what we are getting, B equals to this one, and at last we are getting mu equals to this one. So this is the important relation, the relation between permeability, relative permeability and magnetic susceptibility. Some important formulas are there. Now, what are the magnetostatic boundary conditions? Those are hard to calculate, I will say. If you see any question in your net paper and you wish to apply some magnetostate boundary condition, then by with full awareness you will apply a, otherwise don't try that question, because there are more chances to get wrong answers. So we will use here Ampere's circuital law in the form of H and I. It will be integral of H dot dl equals to I enclosed. That is the same formula we have seen. And the current enclosed by the path is, this K is your current density. You can see here, this is a diagram. If it is a surface, if it is, we can say a separator. This is your medium 1, this is your medium 2, and this is the boundary separating these two mediums. Okay, and we wish to calculate magnetic field susceptibility, etc., on point A, point B, point C, and point D. Okay, so we have to we have to calculate some components, like the parallel components of magnetic field and the perpendicular component of magnetic field. Like for H, it will be normal component, normalization of magnetization, and the transverse component HT, HN and HT. So for these 4 points, just make 4 paths. This is your path 1, this is your path 2, this is your path 3, this is your path 4. So close integral H dot dl will be integral A to B plus C to D plus B to C, C to D, D to A, H dot dl. Let's suppose it is equal to K delta W, because we know I enclosed is K delta W, current enclosed by the closed path. Okay. For path 1, A to B H dot dl, A to B, it is in the medium 1, and in the medium 1 and in the transverse condition we have to use HT1. So we are writing HT1 AT and DLAT, that all the transverse components, and I am getting this one. We will do similar for path 2, again for path 3, again for path 4, and what we will do at last, we will add them all. By adding them, we will get these types of results. Yes. Close integral H dot dl equals to HT1 minus HT2 del W. So if I enclose this K del W, and the tangential component HT1 minus HT2 transverse, nahi, tangential component. I have told you transverse, na, T means not transverse, it is tangential. So HT1 minus HT2 equals to K. So what we are getting, closed integral H dot dl equals to K delta W, and this was equals to your I enclosed. That means we are getting the general equation, so that these boundary conditions will satisfy all the phenomena of both the mediums. So there are some special cases if surface current density K equals to 0. So we have HT1 minus HT2 equals to K now. If K is 0, so HT1 equals to HT2. So the tangential magnetic field intensity is continuous across boundary when surface current density is 0. So we know that B equals to mu naught mu r H. So H equals to B upon mu naught mu r. And using this equation for HT1, BT1 mu naught mu 1. For HT2, BT2 mu naught mu 2. And therefore, if we have two mediums, so one medium having different permeability, mu1 like 5 and mu2 like 7. So if mu1 and mu2 are different, then the magnetic field components, the value will be also different. BT1 will not be equal to BT2. Okay, so the tangential component of magnetic flux density is not continuous across the boundary. This is the second boundary condition. This is the first boundary condition. Moving ahead, we will use now Gauss law for magnetostatic field. And for solving this one, we are now generating a cylinder having medium 1 having mu1 permeability constant, having medium 2 mu2 permeability constant. This is your Gaussian pillbox, we can say. And we have to solve in the same manner. And by normalization, we are getting Bn1 equals to Bn2. So normal component Bn1 equals to Bn2. We see that normal component of magnetic flux density must be continuous across the boundary. Third boundary condition. And we know that B equals to this one and Bn1 equals to Bn2. So we are getting Hn1 is not equal to Hn2 now, because mu1 and mu2 are different. So the normal component of magnetic field intensity is not continuous across the boundary. This is your fourth boundary condition. I hope you are getting my points. So there are four boundary conditions. And what are those? First one is Ht1 equals to Ht2. Second one is Bt1 not equals to Bt2. Third one is Bn1 equals to Bn2. Fourth one is Hn1 is not equals to Hn2. And this is the numeric question. You can solve it and tell me whether you are able to understand or not. Now, we'll do some questions from our previous year papers. And this is our question number 1. An infinite solenoid with its axis of symmetry along the z direction carries a steady current I. The vector potential A at the distance r from the axis is. We have to calculate the value of vector potential A. This is your solenoid type of symmetry. So for a solenoid, we are conventionally getting a symmetry of a cylinder, and the direction it is given in the question, that direction. So the current is in this direction. Okay, current is steady. The solenoid having the radius r, and there are four options. First one is constant inside and varies as are outside the solenoid. Varies there are inside and constant outside the solenoid. Varies as 1 upon r inside and r outside the solenoid. And varies as r inside and as 1 upon r outside the solenoid. This question was from NET December 2012. So what is asking in this question, that for a solenoid, you have to tell that the vector potential A, how it is varying. Is it constant inside and proportional to R outside and the rest 4? So yes, how we can get the vector potential from a magnetic field? We know the magnetic field for a solenoid now. So at a distance r from the axis, close integral A dot dl equals to close integral S del cross A ds. You know this. This is the Stokes curl theorem. Okay. And I have also told you that del cross A is equals to B. Yes. So this one will be equal to this one. Let radius of solenoid is r. Then inside we will cover all the area. So area will be pi r square. So close integral A dot dl will be A into 2 pi r. For the circumference, for this with respect to A, we are using circumference, and for area, we are using area of the circle. So these two will be equal, and putting these two equal, we are getting the relation between A and B. A equals to BR over 2. But we know for a solenoid, we have this standard formula. B equals to mu naught Ni. So just put the value of B here. You are getting A equals to mu naught NIR by 2. And thus you are getting that A is proportional to R. This is inside the solenoid. So first one we are getting. The second one we have to also calculate outside the solenoid. So for outside the solenoid, the instead of this capital R, we will just put a small r, and the same result we can get. So for outside, the A is proportional to 1 upon r. So where is r inside and 1 upon r outside? This will be the answer. It was quite easy question, and these types of question you have to practice more and more. I am sending you assignments day by day. I have posted 2 assignments on your drive of electrostate. 2 assignments I will also post of magnetostate 2. So guys, do practice as more as you can to get the good results. Yes, here is question number 2. A horizontal metal disc rotates about vertical axis in a uniform magnetic field point up as shown in figure. A circuit is made by connecting one end A of a resistor to the center of disc and the other end B to its edge through a sliding contact. As the current that shows through the resistor is, we have to calculate the current in this resistor. um, you may take this question as it is the part of electronics, but no, it is not the part of electronics. It is pure electromagnetics. This is a metal disc. It is rotating in this direction. You can see the direction of arrow. Okay, and having the same uniform magnetic field B. Okay, we are making a circuit because we know for a moving charge there is generation of current, and that is why we are making a circuit. So some current is generating and that is reaching to this resistor, and we have to calculate the value of current. Sorry, we have to calculate the direction of current only. There are four options: 0, DC from A to B, DC from B to A, and AC. This question is from NET December 2013, and this is the recipe to follow. Due to rotation, force on electrons means negative charge. So F will be, you know, the Lorentz force formula. It will be minus LV cross B. So hence center is negatively charged because we have electrons. Okay, so the center is negatively charged and edge is positively charged. If a negative at center, it will induce positive on the surfaces. I have told you this thing in last lecture too. Okay, so positive charges on the surface, and that is why what is the conventional flow of current from positive to negative now? So the current will flow from this direction to this direction, like the current will flow from this direction to this direction. Okay, so from B to A, and the answer will be C, DC from B to A. Next question. The force between two long and parallel wires carrying currents I1 and I2 and separated by a distance D is proportional to. You have to calculate the force between two long parallel wires. You can calculate, I think, now because we have studied this topic now. So this question was from NET December 2013. So you know the formula for the force between two parallel current conducting wire, that is F equals to mu naught I1 I2 upon 4 pi dd is the distance between those two wires, which is given in your question. So this is the diagram. So looking at this formula, you can directly conclude that it will be proportional to I1 I2 upon D. So the correct answer is option number A. It was quite easy question. Next question. A charged particle moves in a helical path. Helical path means we are talking about solenoid. Under the influence of a constant magnetic field. The initial velocity is such that the component along the magnetic field is twice the component in the plane normal to the magnetic field. Okay, the ratio 1 upon r of the pitch L to the radius r of helical path is, we have to calculate the ratio. The ratio L upon r of the pitch L to the radius r. This is not 1. This is r, the conventional length and the radius of solenoid. Just look and convert it into L. Yes, and there are four options. This question was from NET December 2014, and by using a direct formula, this is the diagram we can use. So by using a direct formula, we can calculate. Correct option will be 2. So just we have to calculate with two components. V perpendicular is V, this one is parallel, not perpendicular. V parallel is V cos theta and V perpendicular is V sin theta. You guys will remember this formula. when any charge moves in helical path now, then there we introduce a concept of cyclotron. I will teach you in my next lecture about cyclotron, what is cyclotron and how this formula is coming. Just here I am using directly the formula, and using this formula I am getting this L, putting again the value of cyclotron frequency, and I am getting this one. So the results are 4 pi. Yeah, we'll discuss this question again in when we will study about cyclotron. For now we are getting the result 4 pi. So yeah, all for today. If you guys have any query, you can ask me. No one wants to ask anything. Yeah,
No,
so we'll conclude here, and yeah, see you soon in my next class. Keep studying, do hard work. Thank you.
thank you, ma'am.
Yeah.